Welcome to a video lecture on the nature of the atom. In this one here, we'll look at Rutherford scattering and line spectra. There will be a second one that follows along in Chapter 30. Both of these videos will cover Chapter 30 with the nature of an atom and the different aspects of what makes it up at a quantum level. So, let us begin. You're probably familiar with Ernest Rutherford, and his experiment with gold foil and alpha particles. What he did was he basically disproved the plum pudding model, because up to that time it was believed that there was just kind of an atom was kind of just this soupy thing where there were protons and electrons located throughout, and it was kind of this little gelatin, whatever you want to describe it. And what he really proved was the nuclear structure of the atom, that there's a tiny, very compact nucleus, and that there's a lot of empty space actually around atoms themselves. And this is in the idea of the electron cloud. This is relative when you think about, like when I say there's a lot of space. But he really just proved that there's a very dense core within an atom, and that's the nucleus. What Rutherford did was he shot beams of alpha particles. Now, an alpha particle is just a helium nucleus. It's the stuff, helium gas. I'm gonna talk like this. So it takes an alpha particle is just a helium nucleus. It has no electrons on it, and what it is it's 2 protons and 2 neutrons for a helium nucleus. And shot those at a thin gold leaf foil, and what he found were most of the particles went through undeterred or anything like that, went straight through the substance, went straight through this foil, but there were some that were deflected almost 180 degrees backwards, and just going completely in the opposite direction. And there were some slightly deflected ones off to the sides in different parts, but for the most part, there were only ones that were just deflected right back, and they went all the way through. All right, kind of jumping around a little bit here, even though I'm following along in the book. Maybe I don't personally, as you can tell, agree with the order that they go in here. But line spectra. Line spectra are like what they really are is a series of different fringes that where there's these different bright fringes given off by each atom. An atom, as we've seen, can emit electromagnetic waves. These waves, and for the most part, we'll look at like the visible light. These waves correspond to a set wavelength or frequency, and from that we are able to determine the amount of energy from them. So as we'll see in a little bit, and actually probably the next video, but where we talk about the different energy states, different atoms have different are able to emit different amounts of energy depending on what state the electrons are in, and this corresponds to different different line spectra here. When you look at a incandescent light bulb, which is an older light bulb, or that's weird to say it's an older light bulb at this point, but whatever, or sunlight, you see what's called a continuous spectrum. All the different wavelengths of light, all the different frequencies right there are all accounted for. Whereas if you look at, for example, a set gas or a single gas or a monoatomic substance, single atom, something like that, it produces light only at certain wavelengths. And this corresponds to the different energy levels within that atom for the different energy states of the electrons. Now, sometimes you'll see this measured in angstroms, which a little bit silly. You don't really need to use it. It's a 1 angstrom is 1/10 of a nanometer, so it's 1 times 10 to the negative 10th meters. So it's just you got to move the decimal place over 1 place to the left to get back to nanometers. So if you think about it, red light's just about 700 nanometers, which here it shows us 7,000 angstroms. So if we look here at a bunch of different gases, and most of these here are based on gases, whereas if we see like potassium, it's a solid, and part of the reason that it produces just a continuous spectrum is the interference between, I wouldn't say interference, but it's the interaction, and there's other forms of energy within a monoatomic solid like this, where there is going to be different wavelengths released, and there's so the crystal structure of it makes it so that it is more of a continuous spectrum than a purely defined thing. But each line here relates to an amount of energy based on the frequency, and from the wavelength you know the frequency, and from that you're able to determine the energy released from a quantum jump. And what this is from an electron. When you excite an electron, it jumps up in an energy level. So if you give it energy, it will jump up to a higher energy state, a higher quantum level. And then when it moves back down, because it naturally wants to be down at a lower energy, it wants to move back to a lower state or towards the ground state, it will release that energy. And that energy release is released in the form of a photon, which gives off a certain, depending on the amount of energy released, it gives you a set wavelength, which corresponds to a frequency and therefore a particular color of light. All right, for tonight, what I'd like you to do for this problem here is I'd like you to solve for the different amount of energies that correspond to each line spectra that you see here for hydrogen. So hydrogen right here, and now this, it's a little confusing, so what I'm going to do is I'm going to read off the actual wavelength as given in angstroms, and you're going to need to calculate through and go through and calculate the amount of energy for each one and I'd like you to do it in electron volts. So I'm going from left to right. The first one is 6,560 angstroms. Then we have 4,860 angstroms. Next, 4,340 angstroms. And finally, 4,100 angstroms. Don't go based off of the bar on the bottom. Go based off of the numbers that I just gave you because I've looked those up and I know that they're specifically correct. So, tonight, make sure to calculate your answers in electron volts. Thank you very much and have a good evening. Second video in a little bit.